Welcome to episode 106, Spotlight, Vulnerability Monitoring and Scanning, focusing on control RA-5. The goal of this control is simple but essential. Find weaknesses before attackers do. Every network, application, and cloud service accumulates vulnerabilities over time. These weaknesses arise from software defects, misconfigurations, or outdated components, and attackers thrive on discovering them first. Vulnerability monitoring transforms that race into a managed process. By scanning systems regularly and analyzing results intelligently, organizations uncover flaws while there is still time to fix them safely. The aim is not to eliminate all risk instantly, but to create a repeatable rhythm of discovery, prioritization, and remediation that outpaces potential exploitation. Building on that foundation, defining scope determines what is in view and what remains outside it. Scope includes hosts, applications, and cloud environments, each demanding different scanning methods. A web server, for example, might require both infrastructure and application layer checks, while a container cluster may depend on image scanning and configuration reviews. Clarifying scope ensures completeness and prevents blind spots where vulnerabilities could persist unnoticed. It also establishes responsibility boundaries between internal teams and managed providers. When everyone understands what is covered, results are meaningful, and scanning becomes a shared discipline rather than a disconnected exercise. Scope definition turns endless possibilities into an actionable plan. With scope defined, the next step is gathering data from multiple sources. Automated scanners provide direct measurements from assets, but external advisories, vendor bulletins, and public bug reports expand visibility. Combining these feeds allows security teams to anticipate emerging issues before local scans even detect them. For example, when a major software vendor releases a critical advisory, monitoring teams can cross-reference inventory to spot exposure early. Data from security information exchanges and vulnerability databases adds context, connecting raw findings to real-world exploit patterns. The richer the data, the more intelligent the response. Comprehensive input transforms scanning from mechanical checking into proactive surveillance. Because data floods in from many sources, normalization is crucial. Different scanners and vendors describe vulnerabilities in their own formats, using varied identifiers, versioning schemes, or severity labels. Normalizing this information, usually through standardized references like common vulnerabilities and exposures identifiers, ensures consistent comparison. Imagine three tools reporting the same bug with different wording. Normalization merges them into a single, accurate record. This step avoids duplication and confusion, allowing teams to focus on true exposure rather than reconciling conflicting names. It also supports analytics, enabling clear metrics on open issues and trends. Normalization is the quiet backbone of effective vulnerability management. From there, prioritization turns raw findings into meaningful action by weighing exploitability and exposure. Not all vulnerabilities deserve equal urgency. Some are difficult to exploit or isolated behind strong controls, while others are trivial for attackers and widely reachable. Prioritization frameworks, such as combining vulnerability scores with asset criticality and known exploit data, reveal what to fix first. For example, a low-severity flaw on a public-facing portal with active exploit code might rank above a high-severity bug on an isolated lab system. This approach ensures resources target real danger rather than theoretical perfection. Prioritization keeps security focused, efficient, and aligned with genuine risk. Authenticated scans provide deeper insight than perimeter-only views. External scans show what outsiders can see, but authenticated scans, performed with valid credentials, reveal the true internal state of systems. They detect missing patches, insecure configurations, and outdated libraries invisible from the outside. For instance, a credentialed scan might uncover weak local passwords or disabled logging that an unauthenticated scan would miss. Though authentication requires care to manage securely, the payoff is accuracy. Balancing external and internal perspectives paints a full picture of exposure. Without authenticated scanning, organizations risk false confidence, believing systems are secure simply because external doors appear locked. Frequency of scanning should align with asset criticality and change rate. Critical production servers might be scanned weekly or even daily, while low-impact systems may follow monthly cycles. The faster a system changes, the more often it should be reassessed. Cloud environments that deploy code continuously demand tighter rhythms than static infrastructure. Setting these intervals requires judgment. Too infrequent and exposure grows. Too frequent and noise overwhelms capacity. The right frequency balances responsiveness with stability, ensuring that discovery keeps pace with risk without disrupting operations. Regular, scheduled scanning makes vulnerability management part of the organization's heartbeat. Equally important are safe scanning windows and throttling controls. Scans generate network and system load, and unrestrained activity can disrupt services or trigger false alarms. Defining approved windows, often during low traffic periods, and throttling scan intensity prevent unintended outages. For example, scheduling heavy credentialed scans overnight protects user experience while maintaining coverage. Safe practices also build trust with operations teams, turning scanning from a nuisance into a routine collaboration. Effective coordination proves that security and stability can coexist. Respecting performance boundaries ensures that vulnerability discovery supports rather than jeopardizes business continuity. Once scans complete, validation separates true findings from false positives. Automated tools can misinterpret configurations or legacy software, so analysts must verify results before assigning tasks. Verification may involve manual testing, review of version logs, or consultation with system owners. Imagine a scan reporting an outdated library that was actually patched under a custom naming convention. Without validation, effort would be wasted chasing phantom issues. Reducing false positives maintains credibility and efficiency, allowing teams to focus on genuine weaknesses. Quality assurance in results review is the hidden cost of accuracy and the secret to sustaining engagement across teams. After validation, findings flow into ticketing systems for remediation, complete with owner assignments. Each vulnerability should have a clear custodian, an administrator, developer, or vendor contact responsible for resolution. Tickets include severity, asset details, and recommended fixes. Assigning ownership turns abstract data into accountable action. For instance, a critical database flaw becomes an assigned task for the database team with a target completion date. Integration between scanners and ticketing tools automates this pipeline, ensuring issues never vanish into spreadsheets. Handoffs that define who fixes what and by when transform discovery into measurable progress. Accountability brings closure. Tracking remediation also means managing compensations and waivers. Some vulnerabilities cannot be patched immediately due to business dependencies or compatibility concerns. In such cases, temporary mitigations, like segmentation, access restrictions, or monitoring, reduce risk until permanent fixes are ready. Waivers document these exceptions, requiring approval and review dates. This balance between rigor and practicality keeps the program realistic. It shows auditors that decisions are deliberate, not negligent. Managing these exceptions transparently reinforces trust across teams, demonstrating that vulnerability management is about smart prioritization, not impossible perfection. To evaluate performance, programs measure backlog size, remediation velocity, and closure quality. Backlog reflects how many findings remain open, velocity measures how quickly they are resolved, and closure quality confirms fixes were verified and sustained. For example, if vulnerability counts drop but verification rates lag, risk may still persist. Metrics reveal whether progress is genuine or cosmetic. Tracking these indicators over time encourages continuous improvement, spotlighting where additional resources or automation could help. Quantitative insight converts vulnerability management from reactive cleanup to a proactive performance discipline driven by data, not anecdotes. Evidence completes the cycle. Exported reports, analyst notes, and verification rescans prove that issues were identified, validated, fixed, and rechecked. These artifacts demonstrate compliance with both internal policy and external standards. They also form the historical record that supports audits and lessons learned. For instance, maintaining before and after scan snapshots shows measurable reduction in exposure. Evidence reinforces credibility by proving that declared progress aligns with verifiable data. When kept organized and accessible, it allows the program to show, not just tell, that security hygiene is improving consistently and demonstrably. In closing, vulnerability monitoring and scanning only achieve purpose when they drive actual fixes. Control RA-5 exists to ensure that weaknesses do not linger unseen or unaddressed. Success is measured not by how many vulnerabilities are found, but by how swiftly and thoroughly they are resolved. When discovery, validation, prioritization, and remediation form one continuous loop, security becomes both dynamic and dependable. The organization learns faster than attackers move, maintaining confidence that every known weakness is on its way to closure. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.